When discussing the zeros of a polynomial function, it's helpful to remember that a polynomial is going to have the same number of zeros as the degree of the polynomial. The degree of this polynomial is 5, as is indicated by the highest power on any of the x's, which means that this polynomial function will have 5 zeros. Now, there are several possibilities for those zeros. The zeros could be entirely real. We could have some zeros that are complex or imaginary. We could also have some repeated zeros, meaning that we get the same zero several times. But whatever case we have, when we combine all of them, we will end up with a total of 5. Remember, the real zeros will generate x-intercepts, but we do not get x-intercepts at any imaginary zeros. In this example, we're asked to find the zeros of the polynomial function, and we want all the zeros, whether they be real or complex. In order to find the zeros of a polynomial, we do the same thing that we would do to find the x-intercepts, which is to plug in y is equal to 0 and solve for x. So we'll plug in 0 for y, which leads us to this quadratic equation, and then solve for x, which we can do by using the square root method. So I'm going to switch sides on you here. X squared is equal to -9, and when we take the square root of both sides, we get a plus or minus on the constant side. So we have x is equal to plus or minus 3i. So let's notice that this is 2 zeros, which we were expecting on a second degree polynomial. But let's also notice that the graph of x squared plus 9 is a parabola opening up that's been shifted up 9 units. And this graph doesn't have any x-intercepts, which makes sense because our zeros were imaginary. Let's do one more example. Again, we're asked to find the zeros. So we plug in 0 for y and solve for x. In order to solve for x, we want to completely factor the polynomial and then set each factor equal to 0. Of course, a linear factor is prime, but let's take a look at this quadratic factor. Are there two factors of 2 that would add to 2? No, there are not. So the quadratic doesn't factor using our AC method, and we'll say that it is completely factored over the reals. Once it's factored, that's when we're going to set each factor equal to 0 and solve for x. Adding 1 to both sides gives us our first 0, which is x is equal to 1. We've already determined that this one doesn't factor, so we're going to put it into the quadratic formula in order to solve for x. So we have x is equal to the opposite of b plus or minus b squared minus 4 times a times c all over 2 times a. So we get 2 plus or minus positive 4 minus 8 all over 2, which is 2 plus or minus the square root of -4 over 2. The square root of -4 is 2i, and this simplifies down to being 1 plus or minus I. So let's collect our zeros in one place and clearly state our answer. X is equal to 1 is one of the zeros, and the other two zeros are 1 plus I and 1 minus I. We got 3 zeros on this third degree polynomial. We can expect this polynomial to cross the x-axis at this real x-intercept. But again, we do not get any x-intercepts at the imaginary zeros.